All right. So today we're going to talk about commonly used negative feedback amplifier circuits. And we're actually going to start with one that you guys may or may not realize you've seen in your previous in-class assignment. Okay. So all of these are going to be generic representations, meaning that I'm not going to give you any resistor values or anything like that, because the goal here isn't really to solve for the output voltage, it's to solve for how the output voltage changes if the input voltage changes or something like that. So our first circuit, and I'll give it a name after we discuss what it does, is this guy, where we are going to have negative feedback, because literally every single one of our circuits will employ negative feedback. I'm going to call this resistor R sub F for my feedback resistor. Here's my output voltage. I'm going to place a resistor here between my inverting input terminal and ground. Let's just call this guy R1 for lack of a better term. And then our input voltage is going to be applied to our non-inverting input terminal. So we're going to analyze this circuit much like we did the ones in class on Wednesday, but our goal here is to figure out V out as a function of V in, and then we can actually take the ratio of those two quantities and define what's called the voltage gain of our system. So if we can identify an amplifier and we know what its voltage gain is, we actually never have to analyze it again because we know it's always going to behave in this particular way. So starting off, we observe that no current can flow into or out of our input terminals because we have a negative feedback amplifier. The voltage present at the non-inverting input terminal is hopefully very obviously V in. And so the voltage here at the the inverting input terminal must also be V in. Applying Kirchhoff's current law, we're going to see that we have V in divided by R1 plus V in minus V out divided by R sub F is equal to 0. And I can move that V out over RF term to the right-hand side of the equal sign, multiply both sides through by RF, and what we'll wind up seeing is that our output voltage, V out, comes out to be 1 plus RF over R1 times V in. Our closed loop voltage gain, AV, is defined to be the ratio of the output voltage to the input voltage. And this is obviously just 1 plus RF over R1. So this is what's called a non-inverting amplifier. Closed loop voltage gain. Excuse me. So this is a non-inverting amplifier. So let's talk about what that non-inverting means, which is going to help us figure out what the hell the non-inverting input pin actually does. So my input signal is applied to the non-inverting input pin of this amplifier. My voltage gain, we can see from our expression there, is always going to be a positive quantity, right? So 1 plus the ratio of those two resistors, it is literally impossible for that number to ever be negative, okay? So in a non-inverting amplifier, our output signal is just a larger version of our input signal. We are providing amplification, okay? If R1 is very much larger than RF, our voltage gain gets squished down to approximately 1, which would make this device effectively what's called a unity gain buffer, which is used to isolate circuits from each other. Okay. So this non-inverting amplifier, it's called that for two reasons. If we put a positive signal on the input, we get a positive signal on the output. So our signal polarity is not inverted. So it's a non-inverting amplifier. Also, we are applying our input signal at the non-inverting input pin. So two things specifically tell you that this is a non-inverting amplifier. The fact that a positive input yields a positive output, and the fact that our input signal is applied directly at the non-inverting, or on the non-inverting input pin side of the amplifier. Because one of the problems that I had you guys work in class on Wednesday was a circuit like this, except that instead of just applying the input signal directly to the non-inverting input pin, I threw a voltage divider circuit there in the middle to kind of make you guys think about how everything's going to work out. Okay, so we can put a resistor network on the non-inverting input side, but as long as our input voltage is on the non-inverting input side of the amplifier, it's going to be a non-inverting amplifier.
What should you call it if R is equal to R1 unity gain?
So if RF is equal to R1, then the gain of this is actually 2. If RF is much smaller than R1, then we have a unity gain amplifier where that just means our gain is 1. So effectively, if RF is a short circuit or R1 is an open circuit, we are going to wind up with a unity gain amplifier. So the next circuit that we're going to look at, and by the way, please stop me if you have any questions, is almost the exact same circuit as this one, except that we are going to swap where we apply ground and where we apply our input signal, okay? So it's going to look incredibly similar. So we'll have our feedback resistor, R sub F. Here's our output pin. Now my resistor R1 is going to be placed between the inverting input terminal and our input signal source. And I'm going to ground my non-inverting input pin. So I just want to recap that this is literally the exact same circuit as we had before, except that we've swapped the positions of where we apply our input signal and where we apply ground. I'm harping on that because in your lab today, I'm going to ask you to make each of these two amplifiers, and you will literally hurt my heart if you bother to completely deconstruct the circuit between them instead of literally just switching two wires to get from one to the other. It does not have to be more difficult than that, so don't make it more difficult than that. The lab is hard enough without breaking everything down. All right, so let's go through our analysis procedure. We know that this current is 0 amps, and this current is 0 amps. By inspection, we can see that the voltage at our non-inverting input terminal is 0 volts, which means the voltage at our inverting input terminal must also be 0 volts. We apply Kirchhoff's current law at our non-inverting input terminal. Damn it, our inverting input terminal, sorry about that. And what we get is 0 minus Vn, so that's going to look like negative Vn divided by R1. And then I'm going to have plus 0 minus V out, so that's going to look like minus V out divided by RF is equal to 0. Move V out over RF to the right-hand side of the equal sign, multiply through by RF again, and we find that our output voltage V out is negative RF divided by R1 times Vn, and our voltage gain, always the ratio of V out to Vn, is negative RF divided by R1. So for this particular circuit, if we apply a positive input signal, we wind up getting out a negative output signal. So this is a inverting amplifier. It's an inverting amplifier because the polarity of the signal changes as it passes through the amplifier. Also, the input signal is applied on the the inverting side of the amplifier. I'm going to keep getting those mixed up, but you guys catch what I'm throwing, hopefully. Yeah. So let's talk about this voltage gain relationship here, right? It's established by just the resistors, much like the voltage gain relationship of the circuit above, except that now we have this negative sign. In a lot of applications, having the polarity of your output signal change from the polarity of your input signal literally isn't going to make any difference whatsoever. So like consider an audio amplifier or something like that. It's literally going to make no difference because the only thing that matters is the peak value of your signal as well as the frequency of your signal, because that's going to be what determines what sound is going to come out of this thing. So having a positive signal or a negative signal literally does not matter at all. One interesting thing here, though, is that because there is no restriction really on what RF and R1 can be, not only can we amplify a signal using this amplifier, meaning that we can make the output signal larger in magnitude than the input, but we can also attenuate an input signal. So if RF is less than R1, the output of our amplifier is going to be smaller than whatever we put in. So we get both amplification and attenuation. The quote unquote compromise that we're making is that our output signal is now the opposite polarity of whatever input we put into the system. Okay. Voltage gain. So A is the symbol for gain, and the subscript V is for voltage. If this were a current amplifier, we would have a current gain, and I'm not going to bother you with transconductance or transimpedance amplifiers yet. Yeah. All right, so these are our two most common amplifiers, okay? The non-inverting amplifier and the inverting amplifier. And actually, the inverting amplifier is way more common than the non-inverting amplifier. Okay. Almost all of the other amplifiers that we're going to talk about today are some variation of these, and actually one of them is both at the same time. Okay. So the next one that I want to talk about is we'll give it a name once we figure out what it does. But it's going to be a variation on the inverting amplifier, except that now I'm going to have multiple input signals applied on the inverting input side. So I'm going to start with my feedback resistor, RF. Here's V out. I'm going to ground my non-inverting input terminal, just like I did before. And now on the inverting input side, I'm actually going to put multiple resistors between multiple input signals, right? So we might have a resistor here. Let's call it R1 associated with some input signal V1. We might have a resistor here, R2, associated with some input signal V2. We might have a resistor here, R3, and an associated input signal V3 like so. And realistically, I can keep on going with this for as many input signals as I want. So as we analyze it, we'll see that there's no current flowing into either input terminal. The voltage at the non-inverting input is 0 volts, which means the voltage at the inverting input is also 0 volts. And now we're going to apply Kirchhoff's current law. So I'm going to add this current, and this current, and this current together. And so that's going to look like 0 minus V1. So that'll be negative V1 divided by R1. Same thing for our second input. So minus V2 over R2, minus V3 over R3, plus 0 minus V out. So minus V out over RF is equal to 0. And then rearranging, we have V out is equal to negative RF times V1 over R1 plus V2 over R2 plus V3 over R3 and so forth. So this is what's called a weighted inverting summer, okay? So the inverting means the exact same thing that we've seen previously. If we put a positive polarity input signal in, we get a negative polarity input signal out, okay? It is a summer because it is adding together our input signals, okay? And it is a weighted summer because each of our input signals gets scaled by a different amount, right? So our input signals V1 get scaled by a factor of negative RF over R1. Our input signal V2 gets scaled by a factor of negative RF over R2, et cetera, et cetera. So each input signal has its own voltage gain that it sees. So if I were going to be an absolute super nerd, I could literally develop a circuit that calculates your grades in this class. I'm not that much of a nerd because I don't want to do that much math. That's what Excel is for, but we could do it. Now, if R1 is equal to R2 is equal to R3, etc., then this actually reduces to the following relationship. V out is equal to, let's call this just R. V out is equal to negative RF divided by R times the sum of V1 plus V2 plus V3 and so forth. In this case, we no longer have a weighted inverting summer because all of the signals have the exact same scaling factor applied to them. Now, this is something that the overwhelming majority of you have probably interacted with, but you have no idea. How many of you own a digital bathroom scale? Or how many of your parents own a digital bathroom scale that you've utilized? A whole heck of a lot of us, right? So in a digital scale, we usually have 4 load cells. So that's effectively just a nickel strain gauge or something that you're able to step on, it mechanically deforms, and that mechanical deformation creates a very small voltage signal. It's amplified by one of these inverting summers so that the weight seen on both sides of the scale gives you your total weight. Well, in a bathroom scale, typically there are 4 load cells, one for your heel, one for the ball of your foot on each side. So 4 of them are added together and comes out giving you your total weight. This is the exact same concept that's used in weigh stations and all of that kind of stuff that you see traveling across state lines. That's just a really large load cell connected to an op amp inverting summer circuit. Practical applications, some of you guys will wind up using circuits like these in your senior design projects and all of that kind of good stuff. Crazy, right? All right, so this is how we perform the mathematical operation of addition of signals, okay? So an operational amplifier, and I probably should have led with this earlier, it has that name because its true job is to perform mathematical operations on signals, right? So thus far, we have seen how we can scale signals, so make them larger or smaller. Now we've added signals. So the next thing we're going to do is figure out how to subtract signals. So here's circuit number 4. And this circuit is effectively a combination of both an inverting amplifier and a non-inverting amplifier at the same time. Okay. So I'm going to call this resistor R. And then I'm going to have another identical resistor R placed between the inverting input terminal and an input signal that I'm going to call V1. On the non-inverting side of things, I'm going to have a resistor R between the non-inverting input terminal and ground, and then I'm going to have a 4th resistor R between the non-inverting input terminal and our input signal V2. So a couple of different ways that we could analyze this thing, one of them being superposition, but you guys don't seem to really care for that, and also it's not really necessary, so we can just analyze this straight up as well, just using all of the techniques that we've been doing, right? So this current must be 0 amps. This current must be 0 amps. What is the voltage present at my non-inverting input terminal? Half of V2, absolutely right. So Brennan has correctly identified that I have a voltage divider at on the non-inverting input side of my device. And because my resistors are identical, the voltage drop I'm going to see at my inverting input terminal, excuse me, my non-inverting input terminal is just half of that voltage V2. So V2 over 2. That means that the voltage here at my inverting input terminal is also V2 over 2. So now I'm going to write a KVL equation, adding these two currents together. And so what I'm going to get is V2 over 2 minus V1 divided by R plus V2 over 2 minus V out divided by R is equal to 0. I can multiply both sides by R and I just effectively get rid of that R in the denominator there because 0 times R is still 0. And so now I just have to move V out to the other side and then add up everything on the left. So I'm going to have V2 over 2 plus V2 over 2, which gives me a whole V2. Minus V1. So this is a differencing amplifier. And it simply provides the difference between two input signals, which can be a useful thing in specific applications. Now, it works out to where our output of this guy is just V2 minus V1 if all of those resistors are identical. If all of those resistors are not identical, then what we'll see is that each input voltage signal gets scaled by a different amount. That can also be useful, but it's a little bit more complicated and the math gets a little bogged down. So this is the one that I'm going to show you guys. But effectively, anytime we want to take the difference of two signals, we're going to need to apply an input on both the inverting side and the non-inverting side of the amplifier to achieve that. Okay. So now we've covered amplification and attenuation, addition, and subtraction. Unfortunately, multiplication and division, not really a thing a single op amp can do. But somehow, differentiation and integration is something a single op amp can do. So we can actually use an op amp to do calculus for us. So circuit number 5 is going to be this guy. Every quarter. Every single quarter. Like, before I go into this, the two circuits I'm about to show you guys, the differentiator and the integrator, are literally like a fundamental building block of practically most electrical engineering. So what I mean by that is they serve a role of performing a specific mathematical operation in analog signal processing, which in and of itself is good because sometimes you don't want the signal, you want the derivative of the signal. So like this is how you can take a square wave and make a triangle wave out of it with an integrator, or vice versa. If you have a triangular wave and you want a square wave, you use a differentiator. So that in and of itself can be pretty darn useful. That's how analog function generators do some of their creating signals and all of that kind of stuff. Okay. But not only do these two circuits fulfill that role, they're also a basic building block of PID, so proportional integral differential control systems. And they are also a fundamental building block of communication systems because they also work as low pass and high pass filters. So these same two circuits really have 3 different roles depending on which aspect of electrical engineering you're using it for. So yeah, I'm a nerd and I get excited about it. And hopefully at some point you guys might too, but that's okay. Okay, so I'm going to put a resistor here in my feedback path, much like we've done before. I'm going to ground my non-inverting input terminal, much like we've done before. But now I'm going to throw you guys a little bit of a curveball, because instead of putting a resistor here, I'm going to put in a capacitor. And I'm going to explicitly show that my input signal is a time varying signal. And so my output signal should also be a time varying signal. Okay. Now, one thing that wasn't potentially made clear earlier is that all of the other circuits, I never explicitly said V in and V out were time varying signals. They can be, they can also be DC signals. DC signals is the most boring application of op amps ever because it's just adding concrete numbers, which definitely has its applications. That's why we have calculators to add shit for us. But adding or subtracting or scaling time varying signals is really more of what the op amp is used for. And we'll see that in the lab. This guy really only works the way that we quote unquote want it to if our input is a time varying signal, because taking the derivative of a constant is just always going to give us an output of 0, right? So before we look at this guy, we need to remember our relationships for current and voltage in a capacitor, right? So the current flowing through a capacitor is C times the derivative of the voltage drop across the capacitor, or we know that the voltage drop across the capacitor can be expressed as 1 over C times the integral from negative infinity to some point in time we're interested in of the current flowing through a capacitor. And I'm choosing to use this integral representation so that I don't have to worry about taking into account any initial conditions on my capacitor voltage. Okay. All right, so just for the sake of argument, before we get started on doing things here, I'm just going to note, I'm going to call the voltage drop across my capacitor as this voltage with positive polarity on the left, and the current flowing through my capacitor will be defined as the current that's flowing into the positive polarity terminal capacitor. And after that, we're really just going to apply the exact same relationships that we've been doing. Okay. So no current flows into either input terminal. By inspection, the voltage at my non-inverting input terminal is 0, which means the voltage at my inverting input terminal is also 0. And now I'm going to do KCL, but I'm going to do it slightly differently. I'm going to say the current flowing in is equal to the current flowing in. So I have a current IC of T flowing in, and that is going to equal to negative V out divided by RF. So I can rearrange this guy. And say that V out is negative RF times IC. And we know that IC is just C times the derivative of our capacitor voltage. So let's make that substitution. So I'm just substituting in this relationship right here. So now I'm going to have negative RF times C times the derivative of my capacitor voltage with respect to time. And the last thing that we need to do is then figure out what the relationship between our capacitor voltage is and our input voltage. Anybody have any thoughts on what that relationship might be? VC is equal to VN. Absolutely correct. So VC is defined as the voltage between this node and effectively ground, because that node on the right-hand side of it is at 0 volts, right? Well, Vn is defined between that same node and ground. So Vn and Vc are literally the exact same quantity. So making that substitution, we have negative RF times C times the derivative of our input voltage with respect to time. So this is a differentiating amplifier. Takes the derivative of our input signal, scales it by a factor of R times C, and also happens to invert the polarity because we did all of this on the inverting side of the op amp. So what do you think we're going to have to do to make this into an integrator? So we could replace the capacitor with an inductor. That would absolutely make this an integrator, but usually integrator and differentiating circuits don't use inductors. And the reason for that is because the tolerance of an inductor is usually much greater than the tolerance of a capacitor, meaning that there's more variation in the inductance value than there is variation in the capacitance value due to how they're manufactured. So it's pretty easy to get two plates of the same size, roughly, and then separate them by some fixed distance. It's not quite as easy to wrap a wire around a core and get the exact same number of turns and the exact same spacing between the turns of the coil and all that kind of stuff to make the inductor values very, very precise. So you could do this with an inductor, but it's typically not done. So instead of replacing our capacitor with an inductor, we're actually just going to swap the position of our resistor and our capacitor, and that will also get us integration. So let's see how that shakes out. So now I'm going to have a feedback capacitance, CF. There's my time varying output signal. I ground my non-inverting input node, and I'm going to place a resistor R here. And then here's my input signal Vn of t. We're going to use those same capacitor relationships that we had up above, so I'm not going to rewrite them. You can just go up in your notes if you want to see them. I'm going to define my capacitor voltage to be the voltage drop across the capacitor with positive polarity on the left and this will be my capacitor current. So the current flowing into the positive polarity terminal or out of the negative polarity terminal. And now we can apply our op amp analysis technique. So we have 0 amps here, 0 amps here. The voltage at the non-inverting input node is 0 volts. The voltage at the inverting input node is also 0 volts. And once again, we're going to modify things very slightly. I'm just going to say that the current flowing in is equal to the current flowing out. So our current flowing in is just our input voltage divided by the resistor R. And our current flowing out is IC. Having a brain fart of how to make this. do what I want it to do. So this relationship is okay. We'll hold on to this one and we'll put a pin in it. Let's think about how our output voltage is related to our capacitor voltage. Anybody have any thoughts on that? So our output voltage is by definition a nodal voltage, meaning that it is measured between the output terminal and ground. So the positive polarity terminal of our output voltage is at the same node as the negative polarity terminal of our capacitor voltage. Exactly right. So the negative polarity terminal is at ground. The positive polarity terminal is at ground. So VC is just negative V out or vice versa, right? So recognizing that, we can say that V out is negative VC or negative 1 over C times the integral from negative infinity to T of our capacitor current with respect to time. And we know that our capacitor current is just our input voltage divided by our resistance, right? So I can move, sorry, that should be C sub F. So I can move the resistor out of my integral, and I wind up getting negative 1 over RCF times the integral of negative infinity to T of Vn with respect to time. So this amplifier performs integration on our input signal scaled by a factor of 1 over RC. All right, so let me be clear here. Genuinely, in this class, I'm actually not expecting you guys to memorize all of these things. It can definitely be useful and save you some time, because if you look at a circuit and can say, I know it's this one, we've already worked out how they behave, so you don't have to do any circuit analysis whatsoever. But hopefully I've also illustrated that actually performing the circuit analysis on an op amp isn't that much of a pain in the ass either. So if you don't want to bother memorizing all of these, you could always derive most of them yourselves very, very easily, okay? For those of you who are getting close to senior design and things like that, like I said, some of these will be of significant use to you, particularly if you're a biomedical engineer, so that you're on the bioinstrumentation track and all of that kind of good stuff. So if your senior design project is all about developing some sort of sensor that can measure some signal, this is the second stage of that project where you amplify that signal so that you can actually see it and do things with it, okay? All of this kind of stuff gets used in electrical engineering, really every class we have. Mechanical engineers will use this kind of stuff in their senior design, and it'll be part of some of your subsequent classes and all of that kind of good stuff too. So anyway. All right, so that is the last that I want to say about op amps. So we have a lab. I've posted the mini lab assignment sheet online. I'm just giving you fair warning, this lab is a doozy. So I want to very, very quickly talk about a couple of things here. Your op amp chip, and if I'm not mistaken, this is actually in the lab assignment sheet, but you guys never read the damn things, so that's why I'm taking the time to tell you this. Is going to be a little black box, literally a little black box. It's going to have 8 legs on it. And there is going to be a notch at the top or a little circular divot at the top or both. It's going to be the notch, this divot, or both. So this is effectively just telling you where to start counting your pins. So pin 1 is always the pin to the left of that notch. And then we go 2, 3, 4, 5, 6, 7, 8, like so, because you're going to be given a pin diagram on how to connect this thing. Well, this is telling you exactly how to count those pins so that you can make your connections correctly. For the op amps that you have, if I'm remembering correctly, this is our output pin. This is our positive power supply pin. This is our negative power supply pin. This is our inverting input terminal. And this is our non-inverting input. So I'm asking you guys in the first part of the assignment to make an non-inverting amplifier with a gain of 3, okay? And I tell you in your assignment sheet that you need a 2 kilo ohm resistor and a 1 kilo ohm resistor, okay? So how do we get a gain of 3 with a 2 kilo ohm resistor and a 1 kilo ohm resistor for a non-inverting amplifier? So for a non-inverting amplifier, our voltage gain is 1 over our feedback resistor divided by our other resistor. So is the 2 kilo ohm resistor in the numerator or the denominator? In the numerator, right? That's going to look like 1 plus 2 kilo ohms over 1 kilo ohm. So our 2K resistor is in our feedback. So that means we're effectively going to connect pin 1 to pin 8 with a 2 kilo ohm resistor. Then we're going to have our 1 kilo ohm resistor and then ground out here. We're going to apply our input signal directly to pin 7. We're going to apply our supply voltages to pins 2 and pins 4 appropriately. And then we're going to use oscilloscope probes to measure both the input signal, which is the voltage at pin 7, and the output signal simultaneously so that we can see what's going on. And if you look over there in the left-hand corner of the room here, I actually have this circuit literally already set up so that you can see everything. It is a huge rat's nest of wires, and we'll talk about why that is in just a second, okay? So this is how the resistors are going to be set up, fairly straightforward. What's less straightforward is how we get both a positive supply voltage and a negative supply voltage from our power supply, because it's only capable of providing positive voltages. So effectively what we're going to do is we want plus and minus 9 volts, okay? So I'm going to set up channel 1 as a 9-volt supply. I'm going to set up channel 2 as a 9-volt supply. And then I'm going to make this point where I've connected them together my ground. And so what that's going to result in is I have 9 volts at this node and negative 9 volts with respect to ground at this node. So that's how I'm going to set up my power supplies and all of that kind of good stuff. And then one last thing that I want to point out to you guys, and I think I show this on the mini lab assignment sheet. So let's look. open the file. Blah, blah, blah. Okay, so this picture right here does look like pretty similar to the rat's nest of wires I have. Notice there's that little green post-it note thing saying ground there, okay? So because the breadboards that you guys are using don't have a big terminal or lug that you can set everything to ground on, effectively what I've done is I've just put a resistor and shorted it out across one of the rails on the right-hand side of the board. So I'm connecting the resistor, both legs of it are on either the blue rail or both legs of it are on the red rail. And the only reason that I'm using a resistor is just because it has long legs so that I can connect everything there. So it's shorted out and that blue rail is effectively going to be your ground, or the red rail, whichever one you choose. The resistor on the right-hand side is what I'm going to call a dummy resistor, and it literally exists just to give you stuff to connect your probes and all that kind of stuff to. It is doing absolutely nothing except providing you somewhere to connect and calling it a ground. Okay. All right, so I think I've talked about all of the quote unquote hard parts of this. So go do it.